Hello, everybody. My name is Preston Holmes. Thanks for joining this webinar. I'm going to be telling you today a few things about what we're doing at Google as it relates to IoT. I'm head of IoT solutions, and what that means is I help our customers sort of figure out how to put together all the various bits and pieces of interesting technology that Google is developing across sort of the spectrum of IoT. So I'm going to go ahead and present. And there's obviously a lot that I could cover, but I'm just going to try and cover a few pieces of interesting and recent developments, some recent launches from the cloud platform side. So I work on the part of Google that helps others take advantage of the infrastructure and technology we've developed. And a lot of this technology comes from Google's sort of initial mission, which is to organize the world's information and make it universally accessible. And as part of that, we've had to become really facile and adept at managing very large volumes of information and very large volumes of rapidly changing information, and have had to build the infrastructure to do so. And this is turning out to be pretty useful in the landscape of IoT, where you have both very large numbers of devices and high volumes of data. The numbers, of course, we all hear about sort of the large numbers. It's sort of pick the billions that you want. And I think today, being an IoT sort of focused event, you've been hearing a lot about kind of definitions of IoT. I don't think there's still a universal consensus. So I'm going to give you very quickly my working definition, which is it's this period of transformation. And that at some point in the future, we may actually entirely drop the phrase IoT. And that is, we all have devices and things that are in our world that are not necessarily connected. And we used to have phones that were not internet connected. Then they went through what I call sort of the ugly duckling phase of transition. And now we just have phones again, and we assume they're connected. And so really, it's this transformation of taking things that are not connected normally and turning them into assumed to be connected that is really what IoT is about. Now, Google's sort of expertise in working with data is really around digital data. And one of the things that I think makes IoT sort of distinctive from other sort of data projects is that this is not information that originates as data. Information that originates as data are things like clicks on a web page or online transactions. This is sort of information that's not born until it's already digital. But for IoT, a big part of the task is gathering that information and converting it from analog to digital. And so in many ways, IoT is a means to an end, where it's the set of technologies that we use to try to digitize some sort of data and information and bring it into a platform where we can then apply what Google's really good at, which is kind of managing the data and information at scale. And as we've built out the infrastructure, one of the things we realized is that it was never going to work well for our developers if they had to worry about where the individual servers that their software was going to run on were located. Because certainly in the early days of Google, data centers were being reconfigured and rebuilt so often that a developer could never really rely on where their actual computer, sort of where their software was running. And so we've really built a pretty extensive control plane around our data center to schedule and run software that's fully distributed across the entire data center as if it were a piece of software written to run on a simple sort of laptop computer in some ways. And when you're running software that's so highly distributed, one of the key pieces of the design is going to be the network. And so we've invested quite a bit in the network. We've even gone so far as to lay our own undersea cables to kind of cross over to continents. And we've put a lot of work into inventing a number of sort of software-defined networking technologies. So these are all kind of milestones within our networking infrastructure and network tooling development. I'm going to pull out one, which is the Jupyter system. It's a switching block. And so this is a way that we can achieve a petabit of bisection bandwidth in the data center. So this is a type of bandwidth that is many, many times the entire internet. But inside the data center, when you're running very sort of high transactional volumes on the software. It's something that you need in order to get the messages from server to server so quickly. Now, this will come back as something that's sort of why this might matter to you as people building IoT sort of solutions and applications here in a bit. So this network is now has quite a bit of installation across the world. So the points of presence are sort of major networking hubs that connect our backbone. The blue is part of our kind of key fiber backbone that spans the globe. And then you see quite a few places where we cache content on the edge close to where people need it. And many of these are places that if you have the need for an IoT device to sort of get on the network quickly, this is how we can cover essentially the entire planet, barring sort of the remote regions, which you're going to need to find connectivity solutions for regardless. But when it comes to areas that are internet connected, we pretty much have it covered. The other thing that Google's done just a lot of academic research in and investment in is in the area of data science. So when Google published a paper about a paradigm called MapReduce in 2004, we had sort of this at the time in 2004, before there was any sort of cloud or customer infrastructure around this, we just published it as academic research. And we sort of left it up to the open source community to implement the patterns. So the open source community saw this pattern and thought it was pretty interesting and created Hadoop around it. Similarly, after we released the Bigtable paper, this led to HBase. And so now that we have more and more customers using our infrastructure, what we're doing more is turning the software into both open source implementations, but also the managed product as well. So these are all now, when you start to see blue hexagons, these are essentially products or services of Google's cloud. And we can recognize that when you're working with data, there's kind of these life cycle patterns that come in where you have to capture the data, process it, store it, analyze, and use it. And we have, again, kind of a range, a buffet of choices, which I'm not going to go into every one of them. But if you think about this left-hand side, that's really where IoT starts from our point of view. IoT obviously goes all the way out to that diffuse and analog information that needs to be captured through some sort of sensor or A to D. On the device, there's connectivity. We basically work with a number of partners on the hardware side. But from our perspective, we really start to pick up right when we talk about capturing the data. Now, what we announced just in the last several weeks is what we call Cloud IoT Core. And Cloud IoT Core addresses specifically that boundary between sort of the cloud side of what Google offers around moving data and storing data and connecting and managing devices. So this is a new set of services. One is a device manager, which can maintain the registry of all your devices. It protects sort of who can create or delete a given device with our identity and access management. It allows you to associate the device with a certain set of device credentials, and then is the source of sort of identity verification. And it further provides a sort of stable storage place for device configuration that will be delivered to the devices when they connect or whenever that configuration changes. And it gives you some operational visibility into the health and fleet of these devices. This list of devices that you can then maintain is then enabled to connect to our new MQTT Broker. And this provides a support for MQTT, which I'll talk again just a bit in a second. But for us, the MQTT Broker is really around brokering the protocol of MQTT and allows the data to immediately get delivered into our pub sub system, which is the sort of bus that provides the route of this data into this. So this is a quick shot of sort of what it looks like. We're pretty much, as an infrastructure company, and Google generally is a very API first company. So everything we do begins with the design of an API. We provide sort of very good standards around API design, and you can discover them and client libraries to use them. The things we also recognize is that you need to provide some visibility and user interface around creating devices and managing them in a console. So briefly, MQTT, I think many of you are probably largely familiar, so I'm not going to spend a lot of time. Why it's become so popular are a couple reasons. One is it was designed at a time and for a use case where devices were extremely small, so it has a very small client-side footprint. It was designed at a time when bandwidth was extremely expensive, and so it's very economical about how information is sent over the wire, largely using sort of binary protocols. And it's a relatively lively protocol, meaning that it kind of relies on a socket style of semantic that's available to have messages pushed to a device with very low latency. Now, if we look at the device manager, the way we organize this, all sort of resources at Google are organized into what are called cloud projects. Projects are just simply sort of an organizational bucket to organize a set of developers around a certain project or a program or an application. And inside that, you can create one or more registries. Generally, you would only really need one registry. We do allow you to create multiple kind of collections of devices if you have a need to do so. And then devices within these registries. And these devices maintain credentials and the configuration. Now, one of the things that's interesting about the way we've implemented the device security is that one of the things Google spends a lot of time on is security. If you sort of follow the sort of SecInfo world and look at who's discovering and publishing vulnerabilities, Google does a lot as far as sponsoring internally a very large team of over 700 people and doing security research. And so what we've come up with for our own services, and you can imagine Google as a company is one of the brands out there that is kind of undergoing constant intrusion attacks, et cetera. So we've just developed a lot of experience around security best practices. And one of them involves credential rotation. So in a device, we actually support an array of 3 different keys at a time, and optionally expiration dates for those keys. So that way you're able to rotate the credentials that a device is using to communicate with the broker. This is still optional because we recognize sometimes on hardware it's not always easy to support these. But we work with hardware cryptography partners to have hardware-based cryptographic identity. The idea here is that we never actually see or store the private key at Google at all. That stays on the device, or that stays in a TPM. And then you only register a public key with the device. So that way the device and the application developer can maintain sort of absolute control. And then the device uses this credential to essentially generate what's called a JWT token. This is a kind of a increasingly common standard for doing authentication online. So this JWT token, as it's pronounced, is passed as the password field when the client connects over MQTT. So that is just a little bit about what the new offering is that we call Cloud IoT Core. That helps this bringing the data onto the cloud. I wanted to now tell you a little bit about sort of what do you do with that data once it's there. I had mentioned MapReduce earlier as sort of a data handling pattern. This is fundamentally a way of taking very large volumes of data and processing it by distributing the work across many workers to each take some part of the work and do their bit of computation and then aggregate their sub bits of work up into a result. And the problem is that MapReduce or Hadoop as a pattern is fundamentally batch oriented. And we realized that there's a lot of uses that required more of a stream processing paradigm. I think this is particularly true of IoT. And if you sort of look at what you're instrumenting in the world with IoT devices, the world itself doesn't occur in batches. The world is this continuous stream of events. And so Dataflow as a tool is something that has certain facilities for working with kind of the complexities of real-world streaming data, and I'll talk about a few of these. But I start off with sort of an example that I think everyone can really wrap their heads around, which is that if you're given the task of aggregating these squares by color, it's a really easy task to do. I mean, you can simply add up all the red squares, and then you add up all the yellow squares, and you add up all the green squares, and you have your result. You're given all the squares in advance. Everything's really straightforward. Now, if this was a very, very large list of numbers, you could sort of divide this work up among a bunch of different kind of worker nodes, and you'd end up with a final calculation either way. The challenge comes when you're dealing with unbounded data, what we call unbounded. And that is that this data is arriving in a steady stream with no obvious end to it. So where do you start doing sort of the computation? Now, the simple approach is you'd say, well, I'm just going to slice these up into windows as it arrives and kind of do micro batches. But one of the challenges in that approach is that most often the reason you're interested in streaming data is it has some relevance to what is actually happening in the world. And when data arrives, it's not always the same time when it happened. So when you think about windowing data, there's a couple different patterns. You can window it into fixed buckets of time with non-overlapping boundaries, or you can have sliding windows to sort of do moving average type calculations. And you can also have session windows. So for example, you might use as a session indicator, if you're tracking a vehicle, you might say anytime the vehicle is going more than 5 miles an hour, and as long as it stays longer than, faster than 5 miles an hour, it will be considered one session until the value of the speed goes back below 5 miles an hour. And that will then give you a window of time over which that vehicle is traveling. So that's an arbitrary session window. But again, these sessions or these sliding windows or these fixed windows are all relevant in the context of really what was happening in the world, not what was happening on the computer when they got to the computer. And the reality is, and this is especially true of IoT networks that might be very slow or very intermittent, is that when an event arrives at the computer may not be very consistent with when it happened in the world. And we refer to this as event time skew. So what you see here is that this dotted line represents the ideal case where when an event occurs in the world, it instantaneously is represented on the system that's processing it. But the reality is, of course, that things take different routes to get to the server, and they arrive in different orders, and they arrive late. And sometimes it's really important to wait for that late arriving information, but because it's unbounded data, you can't know at the server when did all the events actually arrive. You could, in theory, sort of wait forever for a late arrival. So there's got to be some method for determining when it's time to kind of give up. And so what we have is really a rich set of sort of syntax in building a processing pipeline that can natively work with these notions of what we call watermarks and triggers. And that is that there's a point at in observing the way data is arriving, which we can make sort of a best effort case around how to compute a given window of time. So for each of these sliding windows, this is a simple aggregate sum for that window. So you can see as the horizontal bar raises. Again, I'm hoping this animation will play for most of you through the tool. But the bar is tracking the current count and sum for these circles for each window of time. And then at some point, it is determining a total. And on the left would be what we call a perfect watermark, which is we emit the total for that window as soon as we know we got the last event. But because we can't know when the last event arrives, we use instead a heuristic watermark that says, based on the way we're seeing data arrive on this channel, we'll make an effort to provide an earlier answer. But this is, of course, tunable, and how late you're willing to wait for something is tunable. And furthermore, the processing language of Dataflow allows for branches in the logic. So you can actually say, I want to have one point of view of my data that is as early and eager as possible to make a decision as close to real time as possible. And then I want another set of conclusions or maybe reporting to include all of the late arrivals, maybe waiting for another half hour to hour, something like that. I'm going to pause here to see a question around PAM and authorization. Client-side SDKs published. So what we're using for our sort of authentication method is we're using asymmetric key pairs. So you can generate these with OpenSSL or any cryptographic library. We support both the RSA 256 and the elliptic curve ciphers. So those are kind of well tested and have good, mature, secure implementations. And then we of course, all of our APIs have a requirement around TLS. So at the transport layer, it's a secure transport. Another question in this block, I'll go ahead and I'll just answer in line. Because yes, we're thinking about the edge. We don't have anything we're talking about necessarily publicly. I think when I get into the machine learning, I'll come back a little bit to some of the stuff we might be doing on the edge with the machine learning. And the other protocols, MQTT is the first protocol for this broker, but the broker itself is designed to support multiple protocols over time. All right, so basically, when you look at kind of complex stream processing pipelines, you want to have some tool that's going to allow you to sort of choose between the batch or streaming mode with one sort of one set of data processing pipeline design. A lot of tools right now, you have to kind of choose between batch or streaming. And then within streaming or batch, you want to be able to control knobs such as accuracy or timeliness and cost. So these are not easy knobs to sort of figure out how the right tool should be built. This is actually sort of the third iteration of a very complex streaming engine at Google. And what we've decided to do in this iteration is actually fully open source the paradigm of how you build the pipeline as a project called Apache Beam. So the idea is that in Apache Beam, you have the client libraries where you build and design the pipeline. And then this pipeline gets defined in a way that can be run against multiple runner implementations. And then what we offer commercially on the cloud side is a managed runner called Cloud Dataflow. Okay, the next topic I wanted to touch on briefly here is machine learning. I think it's, machine learning, to be honest, is kind of rapidly displacing IoT at the top of the hype curve. So now we can all be happy that IoT is no longer at peak hype. And maybe we're still getting there with machine learning. By way of just anecdote, my background, my previous life was actually research neuroscientist. So to me, it's interesting to look at the truth and reality and where it's different from the wetware of actual biological neural networks. There are definitely similarities, and the term neural networks is pretty reasonable to apply to the way this technology works. But essentially what you are doing in a neural network is taking the inputs, looking for various features that you can see in those inputs, and then using those features to build higher and higher order features until you can recognize something that is much more discrete or semantic. So for example, if we input a bunch of pictures, the first layer of neurons, these red ones, might be simply looking for areas of darkness or lightness. The second layer of neurons, these yellows, might be looking for things that are more around, say, horizontal or vertical lines or curves. And then as you build lines and curves into basic shapes and outlines, you can continue to sort of recognize more and more complex features until the final one basically is a classifier that says, what do I see in this picture? So in the end, you get something that can sort of predict something like this. Now, it's important to recognize that in machine learning, this is not a clear and procedural deterministic process. It always has a probabilistic element to it. So any picture of a cat will not result in a 100% confidence in that this is a cat, but you try to build a model that's got enough accuracy that you can actually do something useful with it. So what you can train can actually get pretty complicated. If you showed enough pictures in the training process to one of these neural networks, you could ostensibly build a model that would tell you whether or not you should hug a given object. This would be looking for features that indicated softness or fuzzinesses or sharp and hard edges. And the inputs don't have to be pictures. I mean, obviously this first example is a picture, but the idea is that things that involve complex and highly dimensional data inputs. So these might be speech inputs or written or typed text, or even really looking at this not from recognizing entities in a picture, but the entire scene and writing a caption. And this is why, to me, the connection to IoT is that when you have potentially many sensor types and many individual sensors or devices in sort of a compound deployment on either a very large piece of equipment or in a space, these are each providing sort of potentially very high fidelity, multiple dimensions across, say, temperature and vibration, et cetera. And this kind of very noisy signal that might have a ton of sampling points in it, it's not always obvious how you're going to find some meaning out of it. And if you have a recording of the outcomes that you're seeking, neural networks are potentially quite good at extracting some interesting signal from that noise. And what we found is that this capability is so powerful that the use of machine learning and neural networks at Google inside our own products has been skyrocketing. So the graph on the left is essentially this sort of grep through all of Google's source code for some of the libraries that we use around machine learning. And you can see the number of directories containing models is just sort of going up and up and up. And what we've realized is that we really need to figure out how to share this capability more broadly. We also realized that, oh no, we're going to consume all of our compute power with training machine learning models, and we need to figure out a way to get ourselves out of that conundrum. And one of the things we've done is we have invested in developing custom hardware for training machine learning models and running the inference of those models. So this is custom ASIC hardware that we now have deployed in the data center, which you can see in the background. And this is optimized silicon for processing the kind of vector, matrix math that is fundamentally the type of operation that's involved at machine learning. And when somebody asked earlier about the edge, one of the things that we're doing with machine learning is I thought I had one more slide on the machine learning part here, but so let me just describe the library called Tensorflow. Tensorflow is our open source sort of workbench for data scientists. And it allows you to build the machine learning models and train them either on your own computer or train them on this kind of custom hardware we run in the data center. And the acceleration difference is substantial. There's two types of acceleration that you're going to get. One is acceleration from the custom hardware itself, right? And you can get hardware acceleration in your own computer from a GPU. Think of this TPU as sort of a GPU on steroids specifically optimized for machine learning. The second way you're going to get acceleration running the training step on the cloud is because we've figured out one of the harder problems of how to distribute a single training job across multiple servers. And those two types of accelerations are going to bring a training exercise for a model from something that might take many days on your own computer to run to just sort of an hour or so on the cloud. To the question as far as this is what was used for AlphaGo, absolutely. So we didn't make it public at the time, but we later did announce that the TPU hardware was part of what was behind the horsepower of the AlphaGo algorithm and model. Now, it also involved quite a bit of kind of know-how and engineering to get that model as good as it was. I think it's probably could be considered one of the most elaborate and sophisticated of any neural network model yet, because the task of winning the game of Go against the humans was considered one of the very hard to achieve challenges. So TensorFlow is also open source, and I guess sort of in summary, I'll say that that's one of the tenets that I really appreciate about being at Google, is that we are very pro open source. We do try to kind of release what we can out into the open source community. We do run commercial services, but I think what we try to do is provide open interfaces, and then what we do is provide the proprietary performance. And if there's one thing that's behind that proprietary performance, it is this sort of investment in the hardware, investment in the networking hardware and technology that runs our data centers. I think we developed some software like Dataflow that is very hard to run as an efficient runner of the Dataflow or Apache Beam pipelines when you don't have the high-speed network in the data center. So the IoT Core product, it is in private beta, so you can go to this page if you want to sign up and start kicking the tires of that. We've got sort of what you'd hope to expect as far as free trial programs and documentation online, as well as whole folks of teams to help with specific projects if you're doing this as part of a company project. So happy to take any questions on the material I covered, or sort of any curiosities you have about the some of the things that. So let me see, Nitin's questions. Yeah, so I tried to answer most of these in line at the time they came up. So client SDKs are published. We're really on the device side, leveraging kind of open source MQTT software. We have some thoughts about the edge, but nothing to say right now. And the broker is sort of a multi-protocol broker. Yeah. I'm glad those who stuck it out felt it was worth waiting for. Okay, integration of IoT and ML now that TensorFlow is here. I think the biggest thing that is still going to be a challenge for people in integrating IoT and ML is the fact that people aren't recognizing early enough in the process that it is critical that you record the signal around what you care about, basically fault codes or optimization measurements, because you have to train a model. If say you have all of this sensor data that you collect, right, from IoT devices, unless you have something to train all of that sensor data to, meaning some outcome, right? Like this is when a machine jammed, or this is when somebody came home into the house, or some event that matters. You can't train a machine learning model until you have both sort of the raw signal data and the sort of label of what you're trying to achieve. And I think a lot of people who sort of start with collecting data and then assume they'll figure it out later, they don't collect that all important label at the first time. So that's one. I think other than that, I think TensorFlow is still as far as the insight goes, we're luckily producing higher and higher sort of levels of usability. So now we've brought in what's called Keras directly into TensorFlow as a easier to use API. And I think it's still not really easy to cross-compile TensorFlow for like ARM architectures. It's possible, but you got to really roll up your sleeves. So any thoughts? Oh good, we're getting some questions. Let me scroll up here. So any thoughts if I can run TensorFlow on edge device? Yes, okay, so this is what I'm just talking about. You can do it, you can run it on ARM. It's actually pretty well supported for Android. And that but it's still something that's relatively rough. As far as horsepower goes, it is a very compute intensive task. So to that end, question about TPU for the edge, that's something that's certainly an interesting topic. There's not much I can say right now. We can work with GPU partners on the edge. So NVIDIA makes an embedded class of GPU. And then there's what I refer to as sort of the hybrid method of taking some sort of action you want to run on the edge and have a local implementation. So you might have your local TensorFlow trained model, and then you might have a hosted TensorFlow model as well. And you basically split the request. One route goes to the cloud and makes a request, and one goes to the local implementation. And then basically you act on whichever one comes back first. And that way you get something that is going to give you the best effort at any given time. If your connectivity is down, you're not non-functional, but the device may just operate a little bit slower. So this website, and then this will also link as far as links to the resources, this URL that I put up there, which is if you go to cloud.google.com/IoT, that's a good place to get started. What Intel IoT processors specifically support this? So right now we're able to run our demos on essentially all of the Intel IoT dev kits. So they're all, architecture-wise, they're all compatible. We have some additional kind of client-side demos we're building out in collaboration with Intel today. And those will hopefully be ready soon, especially, certainly they'll be out and widely available by public beta. One of the things I didn't include in scope for this talk, but I can mention is that if you go to, and let me make sure I pull up the link here. One of the other IoT projects that's coming out of Google that we sort of integrate with is Android Things. And this is basically a flavor of Android specifically targeted at IoT development. And this is another area of very active kind of engagement with Intel. In fact, Intel's been involved from the very, very early days of Android Things when it was first called Brillo. What is Google doing in IoT agriculture? So again, one of the things Google as a company does, and I think you know this, but just to clarify, we don't ourselves bring vertical targeted solutions to market as a company. We're sort of providing developers and companies the infrastructure and the software and the tools. To that point, we do have an example published out there around Land O'Lakes and their use of IoT in Google Cloud. Let's see if I can find you that link. And then there's a number of others that I can't yet talk about publicly, but. So yeah, as far as the current private beta and the pipeline of getting people approved, we are doing that in phases. As you can imagine, after a launch, we've had many requests, and we're kind of working our way through the backlog. So I will say, right now we're prioritizing kind of larger, significant investment from companies around commercial projects. I don't know for IoT Laboratory if you're doing something exploratory or commercial. If you're doing something commercial, let me know, and we can try to bump you up on the backlog. So I'll just sort of share my email, which is ptone@google.com. I'll type it. Just know, folks, if I do get quite a lot of emails, so there you go. Do your dev kits support IoT hardware like the low-end boards such as ESP8266? Yeah, so one of the partners we're working with specifically around some of the MCU class boards is Mongoose OS. I personally have been pretty pleased with their developer experience, and so they support both the ESP8266 as well as the ESP32, and I believe it's some either NXP or ST boards. I can't remember which. I think in general, one of the challenges still around the smallest classes of devices is that it is not easy to have them be capable of some of the security standards that Google has at the protocol and the API level. So if you get into truly small constrained devices, you're going to end up needing to incorporate probably some sort of dedicated crypto coprocessor that can handle the signing and signatures that are needed to authenticate both to the service, but also for TLS. And I'm assuming by hard environments, you mean kind of extreme conditions of high temp or acidity or other environmental conditions. And there are some specialized ruggedized hardware boxes out there, but they're obviously a lot more expensive for prototyping. But at the end of the day, they're going to be places where you simply need to use some sort of long wired remote sensor and not try to put the device itself directly in the environment, if you can, right? And that's not always possible if you're talking about a sort of general field deployment. But if you're talking about it as it relates to a piece of equipment or machinery where the harsh environment is constrained in sort of like some sort of chamber, then you'll have to sort of sort that out. I don't think this format's really conducive to kind of me asking you all as many questions as I'm curious about, but I'm curious so far if people who are engaging, at least now, are working more in the kind of industrial side of things, or commercial and commerce, such as retail or something, or more in the smart home environment. Yes, we have both training and startup programs for Google Cloud Platform. The one thing is, you'll see Google appreciates kind of simple and straightforward URLs, but you still got to know them or find them. So happy to paste them in. Yeah, it's a good question. I think there's a startup program. It's not IoT specific. I think what we need to do is we don't have a great we just don't have the bench to do a lot of deep consulting with startups. We do have some partner networks, and I think what we do need to do is kind of gather what are the sort of self-service resources that are missing. So I'm particularly would be interested in knowing from that point of view where what we have in terms of documentation or samples isn't meeting the needs. And certainly if it's a particularly key or juicy project, there's always people available to kind of step in. I think Google, like anywhere else, you'll find people that overextend if it's something that they can get, a bit of a 20% personal or passion project into it. Yeah, so there are, one of the good things about the way Google APIs are built is that there's no there's no need to kind of purchase any license or contract to start trying them. I think with the Maps APIs, there's some very easy to get started guides. OpenShift. I think when you talk about OpenShift and then by extension Kubernetes, and then by extension from Kubernetes, you talk about Google Container Engine, I think that's where you'll have, at the end of the day, some aspect of an IoT solution that's managed through sort of serverless and managed services that a platform might provide, but you're always going to have the domain application and its associated services. So I think OpenShift is a great platform as a service for building some of the domain-specific application services, things that are going to handle front ends and dashboards, et cetera. How those are particularly IoT specific, to be honest, I think a good application framework is a good application framework. It doesn't need a lot of features in it that have to be IoT specific. Great, thank you, Grace, for kind of connecting dots for Intel 2 on the startup. And one of the things that we're pretty, in active development with, I think we're just getting started in terms of what we ultimately will get to is sort of a joint developer program between Intel and Google for IoT. So I ran a 2-day boot camp at our conference in San Francisco in March, and we had Intel come in and do sort of a 2-hour segment in that, and that worked out really well. So thank you, everyone. Thanks for sticking out through the end of the day. Hope it was rewarding for you, and look forward to seeing the cool stuff that you're all building. Thank you.